Hi, welcome back. In this lecture, I want to talk about how to train quantum neural networks. We have been seeing quite different pieces, and now I want to put everything together. So the goal of this video lecture is to understand how we get gradients for quantum neural networks and why they can disappear, so-called barren plateaus that gives problems during the training of the quantum neural networks. The focus of this lecture is on gradient computation for expectation values. In particular, we're going to look at the three basic techniques, especially one that is quantum, which is called parameter shift rule. And I will finalize talking about some of the problems that might occur during the training of the quantum neural networks. And we also discussing some of techniques to avoid this barren plateau issue. So the slide here present in a summary what is really the loops during the training, the different iteration. So we start with our input, that is one data item from our dataset, typically consisting of different features. We have a feature map first and then a variational quantum circuit. As an output of our quantum neural network, we take a measure. Typically, this is an expected value of an observable. And the observable and the measurement of this expectation variable is what we call Y, the so-called model output that depend on the data, the data items, and also the parameter of our quantum neural network. We have it here. After we calculated that, once we got the measurement, we can calculate the loss function given what is the label and what is the error with respect to the label. So this is one for a step. What we typically do in quantum neural network is to have a classical optimizer here in the loop that calculate the new values for theta and introduce them into the parameterized quantum circuit. So we use the classical optimizer, maybe a gradient descent, Adam, to update the theta values using the gradients. These are the gradient of the loss function with respect to the parameter themselves. Remember, these thetas are the angle parameters of some rotation gates and are equivalent to the weights and biases of the classical neural network. So why gradients are important? Well, these are important not only for quantum neural networks, but in general for all the gradient-based learning technique used in neural networks. So gradient tell us how to change the parameters, in our case, this theta rotation, to reduce the loss function, both in classical and quantum neural networks. Without being able to calculate accurate gradients, training can be very slow, a so-called noisy gradient problem, or can even deadlock or stall. So the gradient is zero, so we have no preferential direction towards minimizing the loss function. So we are almost randomly go through the optimization landscape. Therefore, we need some practical methods to estimate the gradients of the expectation value coming from quantum circuits. We also need circuits and measurement choices that avoid vanishing gradients, a so-called barren plateau, that we have no preferential direction during the training of the learning mechanism of our neural network. There are three basic techniques to calculate gradients in quantum neural network. First one is using numerical gradients. Second one is as the classical neural network automatic differentiation. And the third one, that is called parameter shift rules, is using quantum hardware. Typically, finite difference and autodiff are useful on simulator. If you also want to use if you want to calculate the gradients on the quantum hardware, then you need to rely on the technique called the parameter shift rule. So let's start with the first technique. This is quite simple. It's called numerical gradients using finite difference. The trick here is basically to calculate our expectation value at one point and then perturb one parameter of a certain displacement, and we calculate the difference with respect to the function in the original point. So we take one point, we perturb the parameter, we do another expectation value, we take the two values and we can calculate the difference. This is akin to a numerical approximation of the derivative in numerics. So for one parameter theta, we can approximate the function derivative with respect to theta just to calculate this arithmetic difference divided by the size of the interval. This is conceptually simple and works for any black box function. So we can run this estimation on the quantum hardware, and then we can calculate these numerical gradients on the classical hardware. However, the major problem is that this is quite sensitive to shot noise, so we need many shots on the quantum hardware, and the choice of the step size is delicate, is kind of arbitrary. The second technique is called autodiff, and that is the technique used in classical neural network. This works only on classical hardware because we have knowledge about the computational graph that is used to calculate the circuit. So each gate is a matrix operation with a known derivative. So we rely and exploit the knowledge of this derivative to calculate the automatic and differentiation. The major limitation is that in order to calculate with autodiff, we need to have access to internal representation. So matrix is state vector, and this is only available within the simulator. We cannot have this access on the real hardware. The third technique is called parameter shift rule. I just want to summarize the brief idea. Well, when typically we have gates that consist of rotation, an X or Z or Y, and these are basically trigonometric function. So there are some identities between trigonometric function, that one trigonometric function is equal to another one with an argument which has a shift. So think, for instance, the sine and cosine. You can think as the same function, but with an argument that is shifted by pi over 2. So what we can do in order to calculate the derivative is to we know the analytical function that is shifted, so we can use the original function on the quantum hardware, and then calculate the derivative. So here, for instance, there is the formula for the parameter shift formula. What is the interpretation? Well, basically what we do, we run the same circuit twice on the quantum device. One theta shifted by minus pi over 2, and one shifted by plus pi over 2, and then we combine the results and divide it by 2 to calculate the parameter shift rule. The main point here is that we can use this estimate directly on the quantum hardware. So this is one of the few techniques that we can employ to calculate gradients on quantum computing hardware. If you are interested want to go more into details on how this is actually working, I highly recommend this paper by Maria Schuld, Bergholm, Gogolin, Isaac, and Kildoran, entitled Evaluating Analytic Gradients on Quantum Hardware. What are practical considerations to consider when dealing with the gradients in quantum neural network? Well, the parameter shift gradients are exact in principle, but expectation values are estimated from finite shots and therefore are affected by noise. So more shot reduce statistical noise, but increase the cost of running the circuit many times. Fewer shot, however, they provide a nosing gradient estimate. So hardware noise, in addition, provides more variability. Even with a good gradient formula, optimizing might be challenging. I want to spend a little bit of time in talking about one of the major problem in training in quantum neural network that has been identified and described in this seminal paper by Jared McLean and others that describe what is the issue of the barren plateau. So today, when you talk about quantum neural network, you always hear about baryon plateaus and how to overcome. So what is a baryon plateau? A baryon plateau is a region of a parameter space. You might think as the optimization landscape where the gradients are extremely small on average. So let's, for instance, look at this picture here. Consider this as an optimization landscape where we have this is a surface, and then we might think about like this plane, theta 1 and theta 2 are the optimization optimization landscape support, and then this surface is telling you what is the values of L, which is the loss function. So if we are in this region of theta 1 and theta 2, which are the parameters that we want to optimize and we want to tune, if you are in a place like this, we calculate the gradient of L with respect to theta 1 and theta 2, and you see the gradient are basically 0. So the optimizer itself doesn't know where to go on this in this space here. So this is very much equivalent to the vanishing gradient problem, also encountered in classical neural network. So to summarize, the baryon plateau is a region of a parameter space or the optimization landscapes where gradients are extremely small on average. The consequence of this are the gradient-based training becomes very difficult and challenging to train, and the optimizer sees almost no slope, so direction, to find a new convenient parameters that minimize the loss function. There are different factors influencing the baryon plateaus: the circuit depth and expressivity. The larger number of qubits, the deeper it is, the more parameter you have, the quantum circuit becomes more expressive, but also much more amenable to baryon's plateau. Also, the type of cost function impacts the presence of baryon plateau. So global cost loss function, which are loss function that acts on several qubits at the global levels, are more amenable to plateaus than local ones. Local ones are the one that either measuring expectation value of an observable on one qubit or a few qubits, while the global one act on the full qubit space. Also, it matters how good we can do the initialization. If you can do a good initialization, typically we can have better trainability. And also, as I mentioned before, there is a connection with expressivity. So typically, large expressibility also means more difficulty in training. In order to overcome this problem, there is a major technique that is called data uploading, that consists to insert again some feature map after the variational form quantum circuit. So typically we have initial feature map and then variational circuit. So what we can repeat is before another variational form quantum circuit, we can repeat the data encoding in the quantum circuit. So the data reuploading technique repeats the feature map at multiple points. So the same input X is encoded in several times throughout the circuit. If you are interested in this technique, I highly recommend this paper, Data Uploading for Universal Quantum Classifier, that you also will find on Canvas. Other strategies to mitigate baryon plateau? One possible technique is to pay a lot of attention on the ansatz, to look at something that has some structural properties like locality, symmetries. So to choose some architecture that might be linked to the kind of data. So for instance, if you know that your data has pairwise correlation, you might want to have this kind of equivalence in your quantum architecture. So always think about ansatz. So different ansatz, they have different response to the baryon's plateau. Typically prefer shallow circuit, smaller circuit, which are expressive but not too expressive to incorporate into the problem of baryon plateau. Design and use local cost function, typically on a few qubits, on one qubits or a few ones, and also be careful in the initialization of your parameters to quantum gates in the quantum neural network architecture. In summary, QNNs are trained with classical optimizers or are inherently heterogeneous. There are three techniques: finite difference, automatic differentiation, and parameter shift rules. And one of the major problems we have in training quantum neural networks is the Barren plateau. This is the last slide of my lecture, and talk to you soon.